Okay, in this video I'm going to talk about the segments between the tangency points of the incircles of the triangles formed by the sides and the diagonals of a quadrilateral. So basically we have an arbitrary quadrilateral, something like that, and we take both diagonals in this quadrilateral, and like there are now 4 triangles formed by 2 sides and a diagonal. So basically this triangle, this triangle, this triangle, and this triangle. So 4 triangles, and we consider the incircles of these 4 triangles. So circle that touches these 3 sides, then circle that touches these 3 sides, then the circle that touches these 3 sides, and finally the circle that touches these 3 sides. So now the theorem says that the segments between the tangency points of the circles on the opposite sides of the quadrilateral are equal to each other. So basically this segment is equal to this segment, and this segment is equal to this segment. So the segments between, so let me highlight it in a different color. So this segment is equal to this segment, and this segment is equal to this segment. Yeah. So let's denote the I'm not even going to denote the vertices, like the points. I'm going to denote the segments, like different segments between the tangency points. So let's say that this segment we denote it by A, and it is obviously equal to this segment. So the tangent, so like if we have a circle, then the 2 tangents from the same point to this circle are equal to each other. So this is equal to this. So therefore, if this is A, then this is also A, right? So this we denote by B, and this is also B. Then this is C, and this is D. So, and then I will denote these segments on the sides between the tangency points as X, Y, Z, and T. And so the theorem basically says that X is equal to Z and Y is equal to T. So that is the theorem, and so let's prove it. So we consider the tangency points to the diagonals now, And so we notice that this segment is equal to this segment, right? So it is a plus x. And then this segment, on the other hand, so from the other vertex of the diagonal to the same tangency point, would be equal to this segment. So it would be c plus y. So okay, let's write this here. So this segment is equal to a plus x, because it is the tangent from this vertex to the same circle, this and this. So a plus x is equal to a plus x, and this segment now is equal to this segment, because it's again the two tangents from the same point, from the same vertex to the same circle. So it's y plus c plus y, c plus y. So then the whole diagonal, the length of the whole diagonal would be a plus x plus c plus y. That is the whole diagonal. But on the other hand, we can express the whole diagonal differently, dividing the diagonal by another tangency point, this tangency point that I select in red. So first we divided it by this tangency point, and now we divide it by this tangency point. So by this tangency point, one part would be this, it's equal to this. So it would be a plus t, so this part is equal to this part. So okay, let me choose another color. So this part is equal to this part, right? And then okay, and then this part would be equal to this part, right? So so one is a plus t, and the other is c plus z, right? So in this equality we see that a cancel with each other and c cancels, right? So what we get is x plus y is equal to t plus z. And we can do the same for the other diagonal. So again, in the other diagonal, so if let me remove now. So the other diagonal, it's divided in two ways by the okay, so we have two tangency points. One is here and one is here, and we have that. So when it's divided, so this segment is equal to this segment. So it's d plus that, and the other segment is this segment, is equal to this segment. Right, so it's plus b plus y. So this is the entire diagonal, and it is equal to, when we divide diagonal another way, when we divide the diagonal as this segment, which is equal to this segment. So let me now remove. So we have two tangency points. So tangent, so this segment is equal to this segment, and this segment is equal to this segment. So so the green segment now is t plus t, and the red segment now is b plus x. So, and when we sum this together, we obtain again the whole diagonal. So we obtain this equality. And again here we see that d and d cancel each other, and b cancel each other, and we get that z plus y is equal to t plus x. Okay, so now we get these two equalities. And we simply, so from these two, from this and from this, we conclude that, so when we sum them together, we get that x plus y plus z plus y is equal to t plus z plus t plus x. So we sum these two equalities together, and we simply get that x plus z plus 2y is equal to 2t plus x plus z. So x plus z and x plus z cancel each other. We get 2y equal to 2t, or y is equal to t. So that's one equality. And now when we subtract again this and this qualities, when we subtract one from another, what we get is so x plus y minus z plus y is equal to t plus z minus t plus x. So we subtract one from the other. We see that y and y cancel each other, and here t and t cancel each other. Right, so what remains is x minus z equals to z minus x, or 2x is equal to 2z, or x is equal to z. So the two equalities that we get is y equal to t and x equal to z. And so if we see here, this is exactly what we needed to prove. So x is equal to z and y is equal to t. And so the opposite, so this Yeah, so these blue segments are equal to each other. X is equal to Z, and then these yellow segments are equal to each other. Y is equal to T. Yeah, like there is a lot of elements on the picture. I had to remove a lot, so it's kind of maybe was not clear what I was showing, but anyway. Yeah, so that's basically concludes the proof.